Case 3, we have 6 more cases remaining for this cantilever beam. For our aeronautical concern, we'll make it this as a end. Remaining terms you learn for your own, right? Case 3, cantilever beam of length L carrying uniformly distributed load. Now so far we have find out the value for only point load. Now we are going for the UDL, right? That is load per unit area, unit length will be run over to entire length. That means the load will be distributed to entire length. So it is not a particular point it is acting. So it is entire thing is acting. So it has it is not linearly when it is curvature different value. So same thing we have to A to B beam fixed end, that is a fully loaded at any distance x we have to find out. So again you have to take a moment, right? See you are listen here how I am finding a moment for this UDL. Ms equal to minus W L minus X into L minus X divided by 2. How this come? First you understand you have to convert this as in a point load, right? Point load, that means this will have a small w that, and this will sense that we are going to find out at Sx, we are going to find out only this portion, right? Only I am taking this load only, right? So for the w into I have to take this distance. This is a load, that is point load. That load will act in the mid of the section. That means L minus X divided by 2. That half of the distance it will act. So this is a force. This is a force. Length will be L minus X divided by 2. So I am adding W by into L minus X is a force into perpendicular distance. This is a distance. That is what I am getting this, and it is M I know EI by EI into d square by dx square is equal to minus W L minus X the whole square divided by this is common to whole square by 2. Right? Now you do the single term integration to finding of slope, theta finding. EI equal to dy by dx equal to this term will get W L by 6, that is L minus X will get 3 into 3 will come, that is minus L minus X, here 3 will come, already 2 will be there, this is minus 3, that is minus plus will come, right? Into C1 will come. You need to find out what is the C1 value. Now you have to apply here you understand what is the use of this constant C. At the free end x equal to 0, but slope also 0. Right? At fixed end x equal to 0, y slope will be 0. If you apply here, you will get a C1 equal to minus W by x cube by L cube by 6. You have to substitute here, you have to make it the final equation. This is not 0. If you apply here, you will get W L cube by 6 value. Right? Now you find out the slope. Now we have the slope. We have to, what is x? We apply x and you get the final value. Right? So x will be the total length of the entire beam is L. You apply for the entire beam for this equation. EI equal to this theta b equal to dy by dx. EI equal to W6 L minus L. That will term will get 0. Remaining term W L square L. This is L cube by 6. So you are getting theta. Theta will be minus W L cube by 6 EI for the cantilever beam with UDL load. So next we need to find out the slope for this beam. So we know the equation formula for this. Again you have to integral once again of this past equation. This equation you have to do once again in integration. For that you have to, if you do the integration means this, if you do the integration 2 times means you will get C2, constant C2. Right? You apply the fixed and boundary condition x equal to 0 and y equal to 0. C2 will be W L power 4 by 24 if you apply here. Then you have to add C2 here. You have the final equation EI y equal to minus W by 24 L minus x power 4 minus W L power cube by 6 into x W L power 4 by 24. If you do this one second integral means that you will get all the 24 6 these values. At B point x will be L, then replacing x will be L in terms of this terms, then this terms will get 0 by L minus S 0, then L power 4 by 6, this L power 4 by 26. If you resolve this, y equal to W L power minus W L power 4 by 8 EI. So we identified theta and y max for all the cases, right? Right? So we are done for the cantilever beam slope and deflection using double integral method of 3 cases. One is cantilever beam with load at tip and load at the varying location, and we calculated the uniform distributed load, slope, deflection, right, using double integral method. You have to remember that for our cases, right? So for using double integral method for cantilever, for fixed beam, simply supported beam, we'll see in the next class. So we have to apply same method for all the 3 cases. For example, double integral method you have to apply for cantilever beam, fixed beam, overhanging beam, simply supported beam, right, like this. So again you have to apply the moment area method for simply supported beam, cantilever beam, overhanging beam, fixed beam. Same for Macaulay's method also you apply for all these beams, right? So you be prepared with any one of the method, you apply for all type of beams and you will get the value. Same value you will get, right? If you have any doubts, ask me, right? Okay, we'll see in the next class. Thank you.